this is a hands-on meeting, sorry, hands-on training, and we will be using the data provided by one of our own. So John Tegan, thank you very much for giving this data, very timely kind of a data, because we've been studying the time analysis, and your data was right, what I needed. So here is the first tab on this Excel. Yeah, by the way, so it is sort of called hands-on class. It will be mostly my hands-on. I think it is the best use of our own time. I will explain a lot of things, show a lot of things, and I will also give you some homework. It is just inside of the um, Excel file. You will see what I suggest you doing on your own at home. If, however, if you would like to follow me, I recommend that you open another tab in Excel and practice and leaving my tabs untouched, so you would not destroy anything by your exercises. So, however, for now, I suggest you just follow me. So this data has a timeline, and it goes over a period of couple years. So let's see, the very end is 320 2020, so it's very fresh. Just a second. Let me go. So it's starting to 17, goes up to March 2020. It has power consumption. By the way, you hear me well, right? Can anyone tell me?
Yeah, comes
Yeah,
through.
yes. Thank you. Okay, so there is a timeline with the stamps. The data comes every hour. I believe John or somebody did a very good job by putting this kind of a group hour, so of 24-hour span, and so we can compare the data that happens in 1 a.m. on multiple days. Very nice of having that. So in columns we have data for different facilities. So BG, so it's kilowatts per hour, and that's another facility, another facility. Also, what is very nice that it is present in this data set is temperature, outside temperature. This is in Philadelphia. This would be humidity. This is in Pittsburgh, I believe, Baltimore. So very nice file with lots of data. And this is exactly what I was kind of sort of warning you, that today we are dealing with the smart buildings. So it's sort of not exactly Internet of Things, but it is very close to. So the sensors generate lots of data. It's huge volume. In this case, it is 1 hour intervals, but I believe it is much more often, and I think it's something been done before already, but I guess this data can be collected, sensors can be pulled really fast. So first thing I did some data exploration. So this is a plot of this data, of this timeline, and I picked up Philadelphia Customs, just one of the buildings, and you can practice with any other one. And the reason I picked it up is because of this gap, and I would like to show you how we can fill the gaps, because as you may remember, or I hope you do remember, that a timeline is very sensitive fabric. We should not destroy it by throwing the data out. So we should kind of fill these gaps. So the next graph is same data, it just stretched further. So you may see, for example, here at the end of my screen, this is like 17,000 readings. Over here at the bottom, it would be like 3,000 points, data points, right? So over here, we see that this sort of kind of blocks are indeed the spikes. And if you can, we can explore it further, and we can see this is like, so those are the days, and those are the, I assume, or my original assumption was that those are the weekdays, and this looks to be the days off. So when the Philadelphia Customs was closed, right? So this is the temperature in Philadelphia area. This is, I try to plot them together, but okay, so let's move to another tab where I pretty much have just the Philadelphia Customs only, the temperature in Philadelphia area, the humidity, and I have applied, okay, applied some filters. So let's kind of look at those filters. And by the way, this is, I picked up the data for 2018. So we have full year. I started a little bit earlier. I started at Christmas, after Christmas, day after Christmas. And the reason I did that, because we will be using filters, and filters have latency. So filters are essentially a buffers. So let's take a look at the formulas for this filter. So for example, this is, I called it smooth 24-hour filter, right? And this is, okay, that's the one. So the formula for this filter is average for the first 24 readings. And the 24 is magic number because it's 24 hours in the day. So I needed the data. So the latency, the filter would start producing data only once it will get full, right? Correct data, accurate data. And so for that, I need to start a little bit earlier, right? So that is the issue of working with the smoothing filters. And actually pretty much every frequency filters, right? So here we have a zoom in on the first few days, and there is like for like working days, then kind of a weekend that looks to be long. And this is, I can tell you, this is a New Year Eve weekend. So then it is a short week after that, because I guess sort of January 1 was weekday. And then there is a regular weekend, and then that goes so further on. So I'm sort of continuing exploration of the data. I made this smoothing filter, 24-hour filter, green one. So here is the label for it. So it looks, then I plotted the temperature. So this like an ugly spot we kind of interested in dealing with. So here I plotted together the 24-hour filter. And I also, this is 24-hour temperature smoothed. And I did the trend line. So let's maybe increase it a little bit, the width, the height, so we can see it better. So we see there is like a pretty good correlation between the trend line and the outside temperature. However, the power consumption is pretty much as if the AC was turned based on a calendar, right? So it's like, so then I, again, for exploration purposes, I increased the time window. And here is the, result for that type of filter. Instead of average, I took max. And look like what we got. So this is the maximum power consumption during the season that air conditioner is turned off. Then air conditioner goes on. We have that kind of a straight line. So we can still produce kind of a use Excel function or any other function to get the trend line over here. And this is polynomial approximation. But what actually it shows is that we can probably be much better off if just we would do it analytically. We would say that from this date to this date, it is this maximum power consumption, or we know the ratio between average and max, right? So kind of a pretty good, well seen over here. So average is 150, max is like 200 something, right? So we kind of we use max, but we will reduce max to average, and we will say it would be draw this straight line over here. From here to here, we draw another straight line over here, and then and it would be indeed very accurate forecast produced analytically, right? So what I would like to just another point to you another time, we use powerful mathematics to create the trend lines, and the trend lines may be pretty good inside of the sample. But in most of the cases, and in particular dealing with time series, we are interested forecasting the future, that is, goes out of the sample. And you may see that at the end, at the corners, so the polynomial regression goes up. And we do not really know how it will behave outside of the sample, but we know it wouldn't be good. So for forecasting of the future, I suggest avoiding polynomial trend lines, and stay linear will work well, but linear will give you one for the year, right? Analytical, as I suggested, was just something created based on the calendar. We explore the data. We realize that that's when is the date when you turn on the AC. So we created our analytical forecast, very simple function, right? And it will give you a pretty good result, all right? So now let's deal with this kind of a missing data gap. So that's, sorry. Okay, so this is all data for 2018. Probably should be done like that. So this is Philadelphia for 2018. So this is, we're dealing with the outliers and nulls, right? So this is actual data. I'm a little bit caught. I may have taken the. Okay, I may have taken the. Let's go here. I may have used the wrong file, but okay, we'll figure out how to deal with that. I will tell you. So I wrote, yes, because this is, I hid the, let me show you how I did it. You know what? It would be easier and better to show you the logic that I used. Do it again. So the logic that I used, I will probably insert. So I created a logic using an if function. And so it is if this cell would equal, we're interested in nulls, right? So this is the null. what, probably too much to kind of would slow me too much. Let me recover the, God, what happens to my Excel? So I wrote the, you know what, I will send it to you later. So I wrote the if function. So if this null, then I would put some value, right? And the value would be, so for example, I would like to go back in history and pick up, so the logic is, let's do the, so here is, here was the gap, right? So here was the gap. So if I am, the value is, that's real data, right? If the value is below, let's say 100, or to be safe, I put like 90 or 80. So no, first we're dealing with nulls. If the value is below, if missing, right? So we're dealing with this, nulls. Then we go 1 week later and pick up whatever was there. And then after we deal with nulls, we will deal with the kind of outliers. And if the number was lower than 90, then we will again go 24 hours, sorry, whatever, 7 times 24. We go back into history and use that number and fill the gaps, right? So that is how the, and I apologize for that. I will send you the formulas, but that's, it's a bad idea doing it during class. Okay, so once I dealt with that, I have created a new data set. Which doesn't have blanks. And I suggest you doing homework and practice with this and feel it a little bit better. So the logic is, I will send it to you. The logic is that you go, if you realize the null in the real data, you go back 20, so because the data is periodical, right? You go to the same day a week later or 2 weeks later, and fill it in. And so now you get something that you can, that would not throw off the filters, that would not destroy the time fabric, right? So now we are, let's talk a little bit more about filters. I mean, are you following me? Do you understand how to reconstruct the missing data, the missing periodic data? Can somebody speak up, please?
Yes, I think I understand.
Okay, appreciate. Thank you. Okay, so we're going back into in this particular case. I mean, it is different for every case how you reconstruct it, but in this particular case, we can always go back and see what it was on the same day a week. And this is probably the best way to reconstruct it. Other ways, if the function will be smooth, you go like, you don't have to go like to the same day a week and the same hour of the week. Okay, so now I would like kind of stop a little bit and talk how the filters work. So this is what we use, and over here is called run-on averages or run-on window filters. It may be average, it may be max, it may be minimum, it may be some other function. But the foundation for this analysis is a time window that moves across your data. So this is showing like this is the window. So it moves from here to here at every step of your data point, right? And at every step of the data point, we compute either run-on average or max value or min or anything else. We may be computing, and later on we'll be doing computing correlation. So this is how how the running windows work. Uh, so you should always remember that these filters have latency, they have buffers. So if it is 24-hour window, so you need 24 values to fill it in. So you have to start either before, or you should be, if your data is just, you have data for 1 year, you don't have the data before the year started. So you should be cognizant that the beginning of that filter data will be wrong, because the buffer of the filter had not been filled in, right? Uh, so yeah, I definitely sent and using the wrong file. Okay, however, I think we have it here. So this is a 24-hour window, right? And with the kind of exception of this kind of data, missing data, it works well. And here we have what it gave us. It gave us the power consumption over the week, right? So here we have days. With the 24-hour window, we now have weeks. And if we use max 100, now we have seasons, right? So the window function is getting longer to extract lower frequencies. Okay, now I introduced the word frequency. Frequency means how fast the data is changing. So for daily fluctuations, this is relatively high frequency. The weekly fluctuations like this is a lower frequency, and seasonal is extremely low frequency. So filters are connected to time, and time is in a reverse relationship with the frequency, right? So we can have a filter to extract the weeks, to extract the weeks and seasons, right, and days. I'm just looking. What we can, okay, so the next thing is that we can do, so first we use this running windows to get averages or maxes or minimum values out of that time window. But we can be a little bit more sophisticated. So on this graph, I reduced the window to 72 data points, right? 72 hours, because we have each data point is separated from another by an hour, right? And so we still see seasonal changes very well, right? But what we also beginning to see, we can begin to see something else, some anomalies discovered by these 72-hour windows. And what those are like a 3 days, either weekends or 3 days like breaks and broke for the customs in Philadelphia. So in this case, it's sort of accidental. We have not been looking for it explicitly, but it showed us 3 days weekends. It actually showed us 4 days weekends too. So I mean, it's okay to change the length of your running window, and that's what I did. It was 100 originally, right? 100 over 100, where it was, 100 over here, sorry, 72 here, 100 over here, right? So this is 96. I got kind of played with all of them. But you can be more precise. You can be more precise and say, hey, listen, I'm really interested in finding exactly 3 days weekend. And here's a technique to do that. We go into our timeline and pick up a long weekend. Just pick up long weekend from actual data. Let's say somewhere here, right? We pick up this long weekend. We pick up with kind of a little bit of a previous day, a little bit of the day of the working day after the weekend, a little bit here, a little bit there, and we come and we take this data and we create this function. And by the way, you can take it and do it out of the actual data, or you can do it analytically, right? And analytically means you just do formula for it, right? So it's equals 100 here, and like this would be like a step, right? You following me? Is it? Am I clear what I'm doing?
Yes.
Okay, thank you.
Yes.
Okay, and then we run the correlation inside of the running window, and here would be our 3-day weekends, and the 4 days weekends are not even showing up. So this is a power of a correlation analysis of correlation filtering, because the correlation allows you to match exactly to the pattern that you've chosen. And again, it's very simple to take. If you know what you're looking for, then you either take it, cut and paste it, and you and for every single, I mean, you just go through your data, and then every single data point you run window, you run correlation. It's sort of a little bit exhaustive, but Excel does pretty nice work for you, and you see correlation number one equals correlation coefficients equals 1. Here are your 3 days weekend, and you know that they would be high correlations when this fronts of this your analyzing function would be coinciding with the actual kind of a actual how to say it, let me show actual data of another day. So you move your window over here, so it might be like that, and that may give you a correlation of like 0.6, right? But you know that you're looking for correlation coefficient 1, and you would be very accurately detecting your 3 days weekends if you're looking for the 3 days weekends. So you want to detect 4 days like weekends or periods that the customs have not been working, you go to another place, or even simpler, you know that this is 24 hours, so 24 times 4 plus a day here, half a day here and half a day there, that's your another function, and you detect long day weekends. So what I'm kind of trying to summarize here. So we can explore, so one way to explore anomalies in the data is by using pattern analysis. And pattern is something that you know what to expect. You create analyzing functions, and those analyzing functions are short data sets. Like for 3 days weekend, it is 3 days worth of data. For 4 days weekend, it would be 4 days of data. And you create those functions, and you run them through running windows, and you would be very accurate in detecting those kind of interruptions in the work of the Philadelphia customs, right, in this case. You may, in the same very way, you may look at any other anomalies. Let's say, and that would be a very good exercise. Just a second. Find, for example, this spike. Create yourself an analyzing function, and it is not that difficult. So you'll take like 2 days one day before that has a max of like 200 something kilowatts per hour, followed by the day that would have 300 kilowatts per hour, and run it through, and the correlation function will show you these days. And actually, I kind of speculate that the explanation may be that this was a cooling season, the AC was working, and then so here it stopped, and then some maintenance was done, and that's probably a test so that it's working after maintenance, and then it was what, winterized, whatever. So I do not know uh, exactly what happened, but this is definitely an anomaly. We have a tool to find it. That would be a correlation analysis done in a time window. Best time window would be like you may take 2 days before, 1 day before, and 1 day of high power consumption, 1 day of low power consumption, and you would run correlation function. You will find the such anomaly with spike during the week. Um, okay, let me. I think I'm forgetting to tell you something here. I make some. I just saw my graphs. I lost them. I would have been better off with PowerPoint. Okay, now it's here. Okay, here it is. Okay, here is the explanation how to, actually that's what I was looking for. So we do have, I would like to stop and talk a little bit more about the run and window functions. So this is the length of the window, and the longer is your window in time, the shorter is the frequency it will pass, because time and frequencies are in reverse. This is so the let's say so the run-in window is a smoothen filter. It's a low pass filter. So 24-hour window, for example, will be here, and 72-hour window cutoff frequency will be here. So what it means is that those are very frequent fluctuations of temperature. If you apply 72-hour window, they would get smoothed. So they're not passing by. So you put 100-hour windows, it may be not exactly straight line, but you make like 2 weeks like worth of data, and it would be very, very smooth over here. The only price to pay is latency. You need time to fill the buffer. So this is very fundamental, and please let me know if I managed to explain it. Okay. So time and frequency relationship is, again, very fundamental, very important to understand. In this case, we're using just smoothened filters. They are low pass filters, but however, they are high pass filters. I do not want to confuse you with those. So this is called frequency filtering, and very powerful, very good results, very reliable techniques. Especially when you're looking for something that you do not know, right? You look for, so like applying low pass filtering allows you to reveal the trends. If you would be applying high pass filters, you would reveal the fluctuations, variances, and so on and so forth. So we just talked a little bit about correlation. So correlation is, so this was time filtering, frequency filters. Correlation is shape, pattern. We know exactly the pattern we're looking for, like this. We create an analyzing function. We find the pattern we've been looking for. So those are frequency analysis and correlation analysis are very, very powerful techniques for time series analysis. Any questions about that?
So in a time series analysis for a building, would it make sense to do a week, 7 days worth of of time to smooth an average week next to an average week?
You don't need to smooth it up. You need to kind of cover the gap, and the gap is like less than 24 hours. So let me get back to that place. So you need to pass over this, right? So you remember that I have somewhere I have like, where is 24-hour window? So this is 72, I think in exploration, right here I have. Sorry, graphs here, no, okay. So this is 24-hour running window. What 24-hour does is it covered the gaps between the working days and revealed the weekends. So trying to, when you're doing a kind of an analysis using the running window, you try to use as short of a window as possible. The longer window, you will get something like that, right? You will skip the details unless this is your purpose. So if you're trying to figure out the weeks, so you probably would be better off with the 24-hour window, provided that, I mean, it's actually the ratio between how much time the ratio between the working hours and the off hours. If people only would be working like in a good bank in Spain, they are open for 3 hours, and the rest they're kind of a siesta and kind of they're not working. So you probably with the kind of 24-hour window, you can probably kill the working hours. You would not see those at all. So a little bit of experimenting always helps, but when you settle on a length of the running window, it should be as short as possible. Did I answer your question?
Yes.
Okay. So where we were here, I think we were here, right? Okay, so this is the relationship I would like you to remember. So frequency, so the longer is the your running window, the less details you would see. The more it will be averaged, the more it would be like for trend detection. The shorter the window, the more details you would see, but you would probably lose the trend, right? So in correlation analysis, we looking for a pattern, and the pattern, I mean, you need to have it. You need to have it before. You need to know what you're looking at. Otherwise, you would not find it, right? So Windows, running Windows give you ability to find what you may not know, right? But correlation analysis only when you know what you're looking for. Here is something I would like to talk. This is a connection, another connection between the time and the frequency. So this is a piece of a chart. So we see these fluctuations, daily fluctuations, and I used Excel function to run a Fourier analysis on it. And what Fourier does, and again, I don't think you would be using it, but you may hear it, and I would like you to be prepared. And this is very fundamental. It's a big, I mean, in my telecommunications school, we spent like a semester on that. But it's exceptionally powerful, and I will explain you why. So So this is the Fourier chart for this time series data. So this is the time, and this is the spectrum, the frequency spectrum. So Fourier is very implementation in Excel is very sort of mathematical, very pure. So it has this okay, this confusing end, but you can always split it into half, and this is mathematical internal symmetries which produces this result. So we are actually what we're looking for is over here, and here we have what we have a frequency, and the frequency is exactly, so it's 0.5. So it gives us this, believe me please on that, it gives 1 day frequency. So it's dominant frequency in this dominant harmonic in this data set. So I think there is easier way to explain it with the kind of a pure functions. So this is the graph on which I have two sine waves. One sine wave, and then the other sine wave, which is 10 times faster than the other one. And here are the Fourier functions for these sine waves. So this the blue one is for the blue, the longer one. And so time is give you the waves, but when you go into the spectrum, all you see is just one, because sine is unique function, doesn't have anything in it. You just have one rod standing, and it is here at 0.2. The more frequent wave, right? Oscillation, like a sine wave 10, right? This one moves this rod to the right. So here it is at 0.11, right? So you have higher frequency, your spectrum would be moving to the right. Lower frequency, it would be moving to the left. So when you do, if you would decide to do a spectrum analysis on this one, so you would say, okay, I have one harmonic, one oscillation over here, and I have another over here. And believe me, so this is for daily and this is for weekly oscillation. So you would see with the Fourier analysis, you would see that there are two periodic processes in that data. One is for daily fluctuations and the other one is for weekly, and this is the about like seven times sorry, the ratios between like 1 to 7, sorry, 1 to 5 would be in this case. Okay, so let me see. I think I have prepared something else over here. Somewhere I did a little bit more. Okay, I think it is here. Okay, so what I did over here, I took a sum. So here I'm showing these two oscillations separately, one and the other. So the red one is sine wave 10, blue one is a sine wave, right? And I think I have a graph. Or I should have a graph. Okay, here it is. Here is the graph. Here is a sum of these two processes. And here is a Fourier transform for those. And there are spikes. This is sine wave, the longer one. This is the longer sine wave going in. and this is the more frequent one. So that connection between time and frequency, and if you have some kind of a data and you do not know if there is any periodicity in it, you can run a Fourier transform, and then you look at the spectrum and you see, and so this is the ideal picture. It is kind of sort of relatively easy to understand, right? The real picture would be more like this, right? And you would see, that, hey, listen, I have one periodic signal, and then I have another periodic symbol. So something to say that reading the frequency charts from Fourier analysis is sort of like reading the X-rays, requires some kind of education and use. I just want you to be aware of that. There are, maybe Excel is not the best tool to do frequency analysis. Python is certainly better tool. And then further development. So Fourier lived in 1800s. So there is further development, there is wavelets and many other things, and you can do a lot of things with your analysis, and you would probably see these words. For the beginning, I would say stay with kind of a running average filters and correlation analysis, right? But do you have any questions about Fourier analysis? Okay, I decided I need to talk about it because it's a part of this data analysis tool pack, and it's kind of a people from time to time use it, and it's important to understand that it's sort of very powerful transformation. So so we looked at seasonality over here, right? We'll look at this exploratory graphs. Where is my data exploration? Oh, okay, no. Right, and I mentioned that you do trend analysis. Excel does very good job, very easy. You should remember it. You click on it, you add a trend line, you pick up which one you want, linear, polynomial, and for time series would very often become like periodic function, because especially if it is like buildings or something that's kind of a do not move that much around the space, right? Not like cars, but temperature. A lot of seasonal things are seasonal or daily, like there is sun coming and going down. So for periodic analysis, you cannot do linear regression, and the danger of using polynomial regression is that you cannot do out of sample predictions, and in very many cases that's exactly what you're interested in. So my kind of approach is plot the data, and you can, this is wonderful data set. You'd see the periodicity immediately, right? You do not even need to do anything like this, right? So you just see it by naked eye. You see that the data is periodic. So how would you do prediction for the out of sample data? So one thing is definitely do it analytically, right? If you see the trend, you can just write logical function. So from January 1 till whatever day is here, you go to this data point, you see the date. This would be like this power consumption from this point of time to this point of time, this would be this power consumption. You have very, very accurate forecast. Provided that the building is not expanded, that the number of people stays about the same, and nothing major things happening to the climate, right? So if you cannot do, if the picture is not that beautiful, is not kind of a self-revealing as this, then you do auto-regression. And auto-regression is very similar. Again, it's a run-in window filter. So it's a frequency filter. The difference is from the run-in window. In run-in window, we take every data points that precedes with equal coefficient 1. We just take them as is, and we do the average of, so let's say we do like run-in window, right? We do average, and let's say that would be our window, and that's we compute the average. So we take every single data point inside of this window, we take it with the coefficient 1. So auto-regression is a little bit more sophisticated. Auto-regression, you take this preceding data elements with different coefficients. And the way to do it is you need to compute these coefficients. And the way to do it, so this is the auto-regression formula. So the value y, and I is the number of the sample, would equal 0.94 of the sample I minus 1 preceding, then this 0.94 in this case preceding by 2 by 3. So those coefficients I have computed by doing the following. I took this data series over here and I shifted it in time. So I copied it, took this, and pasted it with the shift in one data sample. And then I did it again, and I did it again. And then I ran correlation functions on the shifted and the original series, and I got these coefficients. And these coefficients did not change at all because the process is sort of slower than one data sample. We have like 24 reasons for the day. And so, and I am kind of lazy to do it like 24 times, but I think for accuracy, probably that's what you should have been doing. And by the way, okay, let's stop here for a second. Do you follow me with this, how to compute the coefficients for auto-regression?
Yes.
Yes, following.
Okay, thank you. So
For more accuracy, we do that 24 times to capture all 24 hours of the day.
right,
Gotcha.
or more. So it's tedious process. So I have a little bit kind of a simplified my life. I mean, cheating a little bit. So I shifted it I shifted it 4 times. So in this case, to cover the 24-hour period, and again, you know why we said 24? Because the periodicity is. So the period is 24 hours. This is a day, right? Day and night takes 24 hours. Another process, it would be another number, right? So over here, I kind of cheated a little bit. Instead of taking like, to cover this 24-hour period, I used like shifting it 1, 2, 3, 4. I skipped four regions, right? And so here is what I did, and here are my coefficients, and here is my forecast formula. And so here are the coefficients. Coefficients are correlation functions between the original one and the shifted, right? So this one is between this series and this series, and then this one between this and this, and the next one is, so it's always between the original and the shifted one, right? So I got the correlation coefficients. So you follow me?
Yes. So
Okay.
if you had every 15-minute data, you could do that um, a whole lot of times to get extremely accurate. Would that be a fair thing to say?
Um, okay. The word accurate is, I would say it would be way more detailed, and just a few. Okay, here is actually an illustration to do that. Oops, sorry. So this is the original data, and this is the forecast data. So the forecast is not as smooth, is not as accurate as the original one, because we cheated, right? Because we just skipped like 4 hours. If you would be doing like every single hour, so it would be more like this, way more like this. So I would say it would be more detailed. Now talking about accuracy is a different thing. We're predicting future, and we're predicting future only based on previous data. So there is, as a predicting future, the forecast may not be accurate at all, because all we took into account was the previous data. We should, I mean, we do not know if the climate is changing around, if the number of people working in the building would be changing around, are there any renovation work going around and they keeping doors open, and so on and so forth. So accuracy of the forecast, we do not know. Well, but we will get with more data, with more kind of a detailed, uh, narrow steps, we will get more details over here. Did I answer your question?
Yes.
Okay, thank you. Okay, so auto regression, just to summarize, it's another time of a running window. Only in this running window, we sum up the, again, the formula is over here. So it's a sum of the previous data points with some coefficients. The coefficients we compute using the correlation functions by shifting the original data, and we actually assess what is the contribution of something that happened like 4 hours ago into that number. And it was, okay, where we did it. So it was like 50%, about 50% here. It was 36% here, 39 here. So it's a computation that gives you the coefficients, and then you sum up with the coefficients. So that is pretty much so all about sorry, the when I compute the auto regression, the important point is where you, from what point you start auto regression. So because that's a filter has latency, you have to give filter enough data to beef up its buffers, right? So I believe, this 500 data points. So I started from point 300, and here is my forecast. And then my forecast at this point ran out of data, because I started at 300. I got enough data to forecast another week, right? And then I ran out of data. Any questions about that? So again, to summarize, so we compute the coefficients using the correlation function, shifting the original data set and computing correlation functions, and then we start the forecast from some point in the past, go into the future, but only as much as we are supported by the original data. So we ran out of original data, and our forecast goes like, um, it's not accurate. It's nothing, right? We just saying we stop. We didn't forecast anything beyond 1 week using this method. Um, there is in new Excel, not Excel 2010, but later Excels, there is a um, actually, and maybe, okay, hold on a second. Let me deal with this first. So there is on a data tab, there is a function called Excel sheet forecast, and that's how it works. And so this gives us the confidence intervals. So this is our original data. Excel did everything. I pasted here the how to find it, right, on a new Excel, not on the 2010 Excel. But what I would like to say is probably there is no need to cry and say we need newer Excel because it gives us accurate forecasting. I mean, look, it is Excel understands the math and it tells you, hey, listen, this is future. Those are the confidence intervals. And all of a sudden, we know that here our average, sorry, maximum kilowatts per hour consumption was about 300. And the forecast in about like, what, couple weeks, it can be 1,000, it can be minus 1,000. And what the hell is minus? Uh, how does Google? Sorry, just a second. There are questions. I actually did not explore forecasting in Google. I don't think it would be any better. I would say um, I'm against relying on these automatic forecasting functions. We do not even know what kind of algorithms they use. I mean, they look nice, they nicely present, but I mean, this is very meaningless forecast. I would say if you do auto regression yourself, at least you know what you're dealing with. You know when your data stops. You know how many data uh, points are in your running window. So you have some control. Over here, you don't. You're completely at the mercy of the Excel. And I mean, it gives you a lot of things, right? But this is just overwhelming you with the data. And I mean, does it help? No, with that much data. So I thought it's important for you to know about its existence. Um, I would say talking about the future. So auto regression is probably the best thing is, or if your process in time can be approximated with the linear trend, then linear trends behave very well in the future. Uh, so, or if you're, how to say it, um, so we been dealing in this case, I'm just thinking about the best. Okay, so this was a periodic process, right? And we so probably the best thing for that would be analytical forecast. You know, when you turn on your AC, if policies would not change, you can predict pretty accurately. The building is still the same, nothing much changes. Looks like the building is pretty well insulated, right? Because here is the change of temperature. It's very gradual. Over here, it just went up, like as if it is digitized, right? And it is in fact. So I would say probably analytical would be better for that. If your uh, existing data suggests that this is like a linear, it can be trend line, growing or reducing, or it is any kind of a monotonous line, like sorry, definitely not polynomial, something exponential or logarithmic, then you can use those trend lines to predict the future. But as long as you see periodic process, you're pretty much limited to autoregression. And with autoregression, I suggest doing manual work, because in this case, you would be knowing what you're dealing with, you know what you, how long is your time window, and what assumptions you made before doing that. But I would say that relying on Excel doing these assumptions on your own probably would not give you a good result. Did I answer your question? Okay, just again to summarize, if this is periodic data, you try to do it analytically first, then you go to do autoregression. If the data is monotonous, like growing or falling, first see if you can do linear regression on it, and or if it is like logarithmic or exponential, but do not do polynomial. Okay, so we talked almost about, I hope I was not too fast, but you have this Excel, and I suggest you practice, and I suggest you practice more with the running windows, and you use the running average, and you use the max function to see what, I mean, take another, the data set has other buildings, and you may be able to find something, maybe some buildings do not use or use electricity for heating too. This particular looks like was using electricity only for AC. So there is something to discover, look for some anomalies. So what I would like also to kind of tell you, there are kind of several books I would suggest kind of reading. I do not know if you've heard about the book, The Black Swan. And this is, I would say it is a statistical and also philosophical book. I believe it was written in 2010. A very interesting book, and it is a lot about predicting the future, right? And Black Swan is like a metaphor. Metaphor is based on the fact that before, so black swans did not exist anywhere before except for Australia. So everyone was considering that all swans are white until somebody went to Australia and met a black swan, and that kind of changed a lot of the perception. When people saw the black swan, they said, "Hey, listen, if we saw the white swan before, why couldn't we infer or assume that this one can be also black?" But before that, it was completely out of consideration, right? So it's a very interesting book. And basically what kind of suggests that kind of look at the anomalies, right? First thing is you have learned a lot from the anomalies, and some of them are clear outliers, like in our case, nulls, or I would say um, yeah, like over here, clearly something was not working, like over here. It's completely out. I mean, some outliers just have to be thrown out. But this over here, that is all of a sudden the, so you see that this is the off days. On the off days, the power consumption went up. So you can, again, create an analyzing function to find those off days. And I think I actually have it. I actually have it somewhere on the data set. Damn it. Actually, I'm pretty sure I have it somewhere there inside of this data set. So you create an analyzing function that reveals this condition, and you can find the days on which of hours, the power consumption was unexpectedly high, and then you can go and ask the building management what you've been doing during these days, right? Have you been, there was some maintenance works, or what was happening? So uh, so again, so this is about, so this book is talking about that anomalies that gives considerably more information than just following the predicting the future based on the previous results. So look for anomalies because they may hit the real answers from what may happen in the future and help you to prepare for something that is not like that kind of obvious. If you would be just extrapolating what you have, you wouldn't get a Nobel Prize for discovering something new, right? Um, Another book is Statistical Analysis with Excel for Dummies. Um, and this one I listed as 2009. And the reason is because it exactly describes the Excel that you have, the JSA version of Excel of 2010. And that's a lot of functionality. Excel is packed with it, and just use it sparingly. And some of the fancy features that came in a new Excel versions, like I showed you, the forecast cannot be exactly trusted. And actually, by the way, I did not show you something, so we go back to this tab. Okay, so here is homework. Almost forgot. Here is suggested homework. Uh, the Excel has the forecast function, right? So forecast, so that is, you can use data like on a scatter plot. So the X would be the known data, and the Y would be also known data. And here are a couple sources that explain how to do that. And I also, um, my interest was when you do the forecast, what are your criteria, right? And people over here, they explain that Excel forecast, they use pretty much least squares for error rate, and that tells you something, right? Least squares are very good for in-sample forecast, but out of sample, I mean, uh, it doesn't work that well. So going back, this is a good book, pretty thick book. So you may use it as a reference. At our days, I think I listed you a source on eBay where you can buy it really cheap, and that gives you kind of a reference manual for you for the 2010 Excel that you have from GSA. And the last one, the eighth one, is a kind of exactly a tweet, like how to lie with statistics. I'm not sure if I've told you about that, but this is just to summarize the entire course, how you can manipulate with the data source to kind of get pretty much any result. And I think it's an interesting book to see because it will give you a perception when you would be reading some statistical data, and you would be asking about the, it would, how to say it, um, make you ask some questions. How did you get this data? How you created your sample on which you kind of base your assumptions? So kind of a, you may even find the PDFs for this book on eBay. It is very inexpensive. So that is pretty much all I was planning to tell you. So I encourage you to explore this data, to work a little bit more with the running windows, with averages, and play with the lengths of the windows so you would get a feeling how the data is getting smoother and how you lose some details and how you get more of them. I would say you can leave the Fourier analysis just as is, unless you would have a need to do it, then you would know how to kind of begin looking for tools. But at this point, I think do not overload yourself. yourselves. So this is all I was planning to tell. So any questions? Okay, then I would say thank you very much. And by the way, if you have any questions about during doing homework or doing some other work, please do not hesitate. Reach out to me and I will try to help.
Thank you very much.
Thank you very much too. So I will send, I think, no, I will review this Excel file. I now think that maybe it has everything, but if not, then I will send another one. And again, thank you for being great audience. Okay, I'm turning off the recording now.
Thank you.
Okay, and the class is adjourned.